Next part of the lectures, there's some very basic concepts. Okay, we just want to recall these concepts because again, they are very important while designing. Okay, so when we talk about improving reluctance torque or things like that, so that depends actually on your LDLQ or inductance, right? So we should recall where does inductances are coming from. What's the synchronous, this what is this LDLQ actually is. Uh, so we'll try to discuss those things a bit, all right? So first of all, most of you are familiar with inductance, right? And definition of inductance, as we all know, the flux linkage over current, correct? Now, we can also calculate inductance in terms of reluctance. If you, I don't know whether you are familiar with it or not, see that the definition, the basic definition is flux linkage over current, right? Flux linkage means number of turns times flux, okay? That's flux linkage. So flux linkage over current. And from our magnetic circuit, we know that flux is Ni, that is your MMF, magnetomotive force, over reluctance, right? So if I replace the flux by Ni over reluctance in my inductance definition, current I will cancel out. This current will cancel out, and then we will have inductance as number of turns squared over reluctance. Okay? So remember this, because this is where we get a different LD and LQ value. Why we have a different LD LQ value in IPM machine. And why we called it the magnetic saliency. All this actually comes from the difference in reluctance in your flux path in those machines. And this is basically can be discussed or described using this basic formula. Okay, inductance is inversely proportional to reluctance. Okay, larger the reluctance, smaller will be your inductance. Okay, but one thing we should also remember is that the reluctance, remember that reluctance is useful as long as we don't have magnetic saturation to calculate even inductance. If you have magnetic saturation, then the definition of inductance is actually becomes rate of change of flux linkage over rate of change of current. Okay? And if we have saturation, then the inductance is no longer constant. So if saturation, your inductance will become function of current. Okay? Higher the current, lower will be your inductance. Okay, so inductance becomes no longer a constant value when you have magnetic saturation. And this is often happens in IPMSM. Okay, IPMSM, if we plot the Q-axis inductance, LQ, versus current, you may see that it is sometimes like this. Okay, as the current increases, LQ reduces. Why LQ reduces? Because of this saturation. Okay, and LQ becomes function of current. LQ is no longer constant. For many, especially in IPMSM, aggressively designed IPM machine with high reluctance torque, this is very common. LQ varies with current. Okay, LD is usually kind of constant. Sometimes it varies, but much less compared to LQ. Okay? So that's your, this inductance, what we are talking about here is the self-inductance. And self-inductance is not LDLQ. You have to remember that, okay? LDLQ is related to your synchronous inductance. So we'll try to remember what is synchronous inductance as well in the next few slides. So in an electric machine, you will have self-inductance because you have the windings and coils, 3 phases. So each phase will have its self-inductance. and then the phases are close by with each other, so there will be mutual inductance as well. So current passing through one winding will induce flux. That flux will link the next winding, which is your mutual inductance, right? So mutual inductance and self-inductance both will be present in a three-phase machine. And this other thing is this Faraday's law, which gives us the back EMF in the machine, right? So in PM machine as well, when this flux will come from your magnet, so whenever the rotor rotates, you get your back EMF, and this flux in case of PM machine is constant. Okay, so we in a PM machine, this is usually given as d lambda PM dt. Okay, so magnet flux over when it is rotating gives us the back EMF of the machine. In case of conventional machine, it is your, if it's a synchronous machine, it's the field current which will produce this flux phi, right? In case of induction machine, this flux will be the mutual flux between stator and rotor. Stator flux induces this flux in the rotor, okay? Then the other thing is the losses. So eddy current loss, as you all know, whenever there is AC flux, so flux changing with time will induce a back EMF as by the Faraday's law, and because of that induced voltage there will be current, and this current is a circulating current which is your eddy current, and eddy current can occur in the material, electric steel, as well as in the magnet. Okay, and the magnet and the steel both are actually conductive material. If you remember in our previous slide, we saw a resistance value of the magnet here in the property, the resistivity of the magnet. Okay, so this resistivity is related to your eddy current loss in the magnet material, okay, or magnet, piece of magnet. So when your motor rotating or magnets rotating, we will have eddy current not just in the steel material but also in the magnet. And we know how to reduce eddy current loss in the steel. We use laminations and stack of lamination. The same concept in fact can be also used for magnet. Okay, especially like concentrated type winding which has been proposed for PM machines, the flux produced by the current have harmonics. So those harmonics may not rotate at the same speed as the synchronous speed. Okay, so because there is a difference in the speed between the harmonics and the rotor magnet, so there could be eddy current loss in the magnets. Okay, and how do we reduce eddy current loss in the magnet? Same concept as we use for steel material. We can segment the magnets. Okay, we just instead of using one single piece of magnet, you can use stack of magnets. Okay, something like this, which can reduce your eddy current loss. If you see in your design there is a issue of eddy current. Okay, but in conventional distributed winding PM synchronous machine, theoretically there should not be any loss in the rotor. Okay, any iron loss. However, that's not true because your flux density, air gap flux density, is not sinusoidal. So there will be harmonics, and those harmonics rotates at a different speed than the synchronous speed. So there is always some losses, eddy current losses. Okay? And there is, so we can reduce eddy current, but we can never reduce actually hysteresis losses. Okay? In your steel material, it's subject to your, when it is AC current, you have positive cycle and negative cycle. So it's always magnetized and demagnetized, the steel material. Okay? And what that means is that it is, this hysteresis loop is forming all the time in a motor. Okay? And so that means there is this hysteresis loss present in a motor. Usually it's very small, but it is present, and there's no way we can reduce it. Okay? It depends simply on the material's property. Okay? You can measure it, but again, accurate measurement of hysteresis loss is also not possible. Okay? So usually what happens is hysteresis loss, eddy current loss combined together becomes your excess loss. Okay? When you measure efficiency of motors, you can account for your copper loss, I square R. You may be able to then find other losses, which combines the eddy current, hysteresis loss, and mechanical loss. Especially in PM motor, we cannot also separate mechanical loss from the iron loss. So mechanical loss and iron loss are clogged together, which you can measure running the motor under no load condition. So if you operate the motor, a PM motor, under no load condition, you can measure how much power it is taking. Okay? The no load means the motor is rotating freely. You're supplying voltage and current. The motor is spinning freely, not coupled to any mechanical load. So in that case, you may think that it should not take any current, or any loss. It should not have any loss, but or should not take any consume very little power, just only I square R. But if you try to measure the input power and do I square R measurement, means current, and then measure the resistance, calculate I square R. So input power minus I square R is not equal to 0. You will have something. So what is that? That is actually the iron loss and your mechanical loss. Okay? So that's under no load condition. So we can measure under no load condition this iron loss and mechanical loss, and we cannot separate them easily. So for PM machine, if we want to separate iron loss from the mechanical loss, you actually need a dummy rotor. Dummy rotor means you make the rotor exactly same as your PM machine, PM rotor, but remove the PM, no magnet. Okay? And then run that rotor and do same no load test, measure the losses, and that loss will be your mechanical loss. So you got the mechanical loss from the dummy rotor, and then you do repeat that test with a magnet rotor, do same thing. Difference between these two losses is your iron loss. Okay, only that's how you can measure iron loss. Okay, so to separate iron loss, you need dummy rotor, and usually people do not do it. Why do you make a dummy rotor just to measure the mechanical losses? Okay, so that's why it's quite difficult to separate iron loss and mechanical loss in PM machine. And in the iron loss, even if you somehow can separate iron loss from mechanical loss, separating eddy current from hysteresis is also not so easy. Okay, you can do it. There are some ways of estimating the KH and KE from their various step of the measuring the losses for various operating conditions. So it's possible, but it's not accurate. Okay, so one of the biggest issues is now like 200 years of electric machines history. but we are still unable to actually accurately measure iron loss, okay, or accurately estimate iron loss. You can do that for no load condition, but in the load condition, this loss will change. Okay, this loss is because there will be saturation, there will be leakage. So we don't account for them when we do the no load test. That's why that it is, even now we cannot actually accurately estimate or measure iron loss. Finite element analysis we can use to calculate iron loss for PM machine. Again, they are on based on a model, okay, model such as this type of equations. So you have they just estimate this coefficient, hysteresis loss coefficient KH and eddy current coefficient KE. So this coefficient, estimation of these coefficients, again, not very accurate. So often finite element analysis, when they estimate iron loss, they always underestimate. Okay, even under load condition, you can calculate iron loss using finite element, but it underestimates. So if you try to match it with your experimental result, it never matches. The experimental loss is always higher. Okay, so why we cannot account for? Because we are not able to estimate these coefficients correctly, or the model is not accurate enough. The iron loss model in the finite element is not accurate enough. So that's another area of research which can be explored. Okay, it's very hard, so people usually, I think, do not want to explore it as much, but it is a need for everyone actually to be able to estimate iron loss accurately. And the last one is the skin effect. Again, most of you know about skin effect. So if we have high frequency, the current density in your conductor becomes non-uniform. Okay, if you have a DC, theoretically current should distribute in a conductor, in a circular conductor, completely uniformly, right? But as the frequency increases of your current, the current tends to concentrate at the outer side of your conductor, right? So the distribution of the current in the conductor becomes non-uniform. So when it is non-uniform, the resistance that we usually estimate for a conductor using the length, cross-sectional area, and resistivity or conductivity. Okay, we can calculate resistance. So this resistance is DC resistance. And this resistance does not account for skin effect. Okay, so if we operate especially motors with high speed or motors with high switching frequency inverters, may see high frequency current, harmonics, etc. Okay, so AC current, so then if we only consider DC resistance, it's not sufficient. We have to also consider this skin effect phenomenon, and skin effect can be accounted for by this classical skin depth formula. Okay, it depends on the conductivity of the material, permeability of the material, and the frequency, angular frequency omega. Okay, this is so with the, if we know that skin depth, then you can calculate a resistance using the same formula, but now your diameter of the conductor is reduced by the skin depth, by delta. Okay, and then using this you can estimate a resistance which is not same as this DC resistance, and this resistance is known as AC resistance, and AC resistance could be important, especially if you are dealing with high frequency. Okay, and like in high frequency, that's why sometimes they propose to use a different type of wire. Okay, that is like to which can reduce AC resistance, because your AC resistance loss could be significant. Okay, and if it's significant, then it can affect your efficiency. So usually in finite element you don't consider this, and then you got a resistance from your finite element, you got a loss from your finite element, and you build your motor and you found that your loss is not matching. So why is not your loss matching? Maybe there was a significant AC resistance which you have not accounted for. Okay, so in design process all this need to be considered. Okay, even during your design, especially if you are optimizing efficiency, then you need to know whether you are doing whether your motor will see high frequency when it is operating with high switching frequency PWM. Will its harmonic see high frequency, and is that going to cause some extra losses, especially in the AC resistance? AC resistance is also uh, a, a concern for the hairpin winding. Yesterday I mentioned about hairpin winding, right? So usually AC resistance in the conventional wire you minimize by using very small cross-sectional area wires, and then use several of them to make a one single branch, right? So if you look at take out any motors and look at their cable, you will see that there are many small branches, right, which are tied together to give you one single conductor. So its region is actually this, to minimize AC resistance. Whereas in hairpin winding we talk about, it's a one single copper, kind of like a pipe, right? So when you have a something like that, hairpin winding, we don't have any option of reducing AC resistance, right? So if you are designing motor for hairpin winding, that means AC resistance must be considered and must be checked whether it is within the acceptable limit or not. Okay? We are supposed to take break here, but I'll skip it. Okay, so from here onward, we will start to look at the as a motor, as a overall concept. Okay, so far we look at as a components. Okay, like the inductance, copper loss, something like that. But from here onward, we'll try to look at it as an overall picture. And for motor, it's what's happening is it's energy conversion, right? You put electrical power or electrical energy, and you want your output is a mechanical force or torque. So it's an energy conversion. And we may want to estimate what is this energy conversion, and how do you do that? Actually by measuring or by calculating the torque that's going to be produced, right? So here in the next couple of slides, we'll be looking at the basic equations of torque calculation, which is again at the back side of your finite element analysis. How the finite element analysis estimate torque. Many of you may have used or planning to use finite element. That gives you a torque result once you put your geometry, once it is process it, gives you a torque. So how is it calculating this torque? Okay, it again comes from quite basic concepts. So just try to refresh. How does the energy conversion happens from electrical mechanical? Always through coupling of a magnetic field, right? You must have a magnetic field. You must have some kind of moving component which tells us that there is a mechanical energy that converted from electrical. Okay, for example, so these are our learning goal for the next few slides. We'll try to interpret the energy conversion. We will try to see that how in a synchronous machine this happens, and then at the end we'll try to get the torque speed steady state equation, torque equation, steady state torque equation of a synchronous machine, but I will show you how it is different in a PM machine. Okay. So as I said, it's basically when energy conversion happens, it's through the coupling of magnetic field. You have one side electrical energy, you will have some losses, which could be in your wires, in your windings, remaining of the electrical energy stores in the magnetic field, okay? And that magnetic energy actually converts to mechanical energy, okay? In between, again, you could have some losses, like in the magnetic field, the loss is in your core, that eddy current hysteresis loss. After it converts to mechanical energy, loss is your friction, etc., the mechanical loss, okay? And whatever remaining is your mechanical energy. And the mechanical energy, this conversion, we can see very simple device such as a relay even, okay? In a relay, we will have a linear movement, so it's a force, it's a mechanical force which has converted from this electrical energy, okay? Whereas in case of motor, it is your electrical energy input in the stator in case of AC motor, and in case of DC motor, electrical energy input into the armature or rotor, okay? And most of you know how to calculate this force and why there is brush commutation in the DC motor, right? It comes from the very basic BIL, correct? Force is equal to magnetic flux, current I flowing in a conductor L, right? So that's where we can in fact use this to calculate out the torque for a DC motor. But we don't use this usually for AC motors, right? To calculate torque or force. So instead what we use start from energy balance equation, and then we can use the energy to calculate the force or torque using the Virtual displacement method, okay? So quite simply here, you can see energy must be conserved, right? We cannot create or destroy energy. So your electrical energy, which is converted to mechanical energy, plus the energy stored in the magnetic field, okay? And we can start from that very basic concept of energy conversion. Now, electrical energy, what is electrical energy? It's your voltage time current is your power multiplied by time, right? Power multiplied by time is your electrical energy. So that's E is a voltage, so E time I multiplied by time, we can express it as our electrical energy. Now, this E is this voltage source, right? So E, we can consider it coming from a rate of change of flux linkage, right? So E can be written as d lambda dt, lambda being flux linkage. And if I replace E here by d lambda dt, then dt will cancel out. This dt cancels out this dt. So electrical energy is also current time flux linkage, right? So electrical energy can be thought of as current time flux linkage. And mechanical energy, all of you know, force time a displacement, right? So in other words, the stored energy in a magnetic field from this equation can be thought of as current time flux linkage minus force time displacement. So this displacement can be Virtual as well. That's why it is called, when we use this equation to calculate force, we call it Virtual displacement method, right? So from here, we can see that force will be equal to I d lambda minus that magnetic field, stored energy in the magnetic field, over dx. Okay. So this is what is written here. Force is I time flux linkage over dx, field over dx. But this equation is not as simple as it looks, because your flux linkage could be function of current and the displacement. Flux linkage can change as the displacement changes. Similarly, field can change. So this becomes a partial differential equation. And so this was given as a force, but if it is a rotating motion, same equation we can write in terms of torque. Okay. So in finite element analysis, actually they try to solve this equation. Okay. If there are different ways, one of the ways is to, if they're using magnetic energy to calculate torque or force, they in fact use this equation, this basic equation that comes from the energy conversion. So they use the try to solve these partial differential equations. Okay. Sometimes they also, this equation becomes simplified. Instead of energy, if we use co-energy. Okay. So for hand calculation, often we use co-energy to calculate force. But in the finite element, once you know flux linkage, and this stored energy can come from, let's say, inductance. So this will be your half Li square. So if we know inductance, so this inductance, this energy can be estimated. This is simply Li, half Li square, magnetic stored energy in the inductance. So they try to solve this equation and numerically and give us either force or torque as we did. Okay. Now, in traditional way of calculating torque in a motor is not energy or co-energy, right? We use a completely different way to calculate torque by hand in a traditional motors like synchronous motors. So how do you calculate it? How do you calculate torque? Anyone remember? If we want to calculate torque of a synchronous machine, how do you calculate it? We calculate it from power, right? So we try to estimate the power, and then from real power dividing it by speed, we do the calculate the torque. So to get power equation, we need that equivalent, electrical equivalent circuit of a machine, and then we use that circuit analysis to calculate the torque, right? So we'll try to recall that and see what is different if it is a PM machine. This is a conventional synchronous machine here you are seeing. You will have a three-phase stator. Your rotor could be either salient pole or cylindrical pole rotor, right? Now the stator for a synchronous machine, a PM synchronous machine could be same, three-phase distributed winding stator. And if I put magnet rotors, surface type or interior type, or I could even use a reluctance rotor, I will get a PM synchronous motor or synchronous reluctance motor. Okay, so construction wise, the stator could be exactly same. Okay, you can even use an induction motor stator and replace the rotor with a PM rotor, and you will get a PM synchronous motor. Okay. In fact, when I did my PhD, I did a PM motor design project. So what we did is we just bought an induction motor, ABB induction motor, because I was only doing rotor design. So I just took out the stator, build my own rotor, put it back, run it, and I have the prototype. So it's very easy to actually construct prototype if you want. Okay, you can, this induction motor, how much it costs? Very little, right? You can go for 1 kilowatt, 500 watt, whatever, small ones, but just make the rotor and you will have your prototype. You can build as many as you like. Especially in India, I think this construction is far more cheaper than what we can do in Australia. It will be very costly for us. But you may make 10 rotors if you want to for one same stator. Okay, so you can replace simply the rotor of an induction or a synchronous motor to get your PM synchronous machine or reluctance machine. The other concept which is very important for three-phase AC machine is that rotating magnetic field, right? If we supply three-phase balance current to our stator without doing anything, if you simply supply three-phase current, you get a rotating magnetic field. Okay? Here you are seeing a two-pole machine without the rotor. You're simply supplying the three-phase current induces a rotating magnetic field. Okay? So for PM machine, same thing. You will be applying the three-phase balance current, but via a inverter. Okay? And you will get this rotating magnetic field. This rotating magnetic field rotates at the synchronous speed, as we all know, perhaps. And the synchronous speed is related to the frequency and pole pairs. Okay, this is a mechanical speed. Mechanical synchronous speed. And if we use the electrical angular speed omega, this is your electrical speed. So often in control, we talk about electrical speed, mechanical speed. So this is where they come from. Whenever there's a synchronous electrical speed, it's simply the angular frequency. Okay? And divided by your pole pair, you get your mechanical speed, mechanical synchronous speed in radian per second. Okay? So we have now, we can have a rotating magnetic field. And this rotating magnetic field is also very important to understand the concept of space vector. Okay? So in control, you may hear about like DTC, etc. We talk about the space vector. So what is this space vector? In fact, the space vector is nothing but that rotating magnetic field. Okay? So if we only supply single phase, our flux or MMF, whatever you take, they fluctuate, go from positive, negative, positive, negative. But if you add all the three phases together, you get a resultant flux which is rotating. And if we look at as a waveform, this black one is your resultant field. Okay, rotating field, rotating MMF, whatever you say. And this resultant field we can represent as a vector. Okay, like any other sinusoidal quantities, this is also a sinusoidal quantity, but it is rotating. And this sinusoidal quantity we can express as a vector. And that's the space vector actually. Okay, it's not some alien concept. It is simply the rotating magnetic field represented as a vector. So if we look at here, A, B, C is your three phases, when we are expressing it as a phasors, and the resulted black one, which is rotating, you can see. So that's your space vector. Okay? So it could be voltage, it could be flux, the space vector, or it could be even MMF. In the concept like DTC, direct torque control, you in fact try to produce this space vector for by switching your inverter in such a way that they give you a particular space vector for a particular torque or flux. Okay, that's how is actually DTC. Okay, so it comes from this very basic concept. So now let's put the rotor in. So if we have the rotor rotating, we will have the induced EMF, right, from the Faraday's law in your stator. So another concept which is again comes from very basic relation of induced EMF is that the flux vector and the back EMF vector, they are always 90 degree to each other. So why they are 90 degree to each other? It in fact comes from the Faraday's law, right? So if we consider the E is, as we know, is N d phi f dt. I'm just ignoring the negative sign here. So if we consider flux phi f to be a, let's say, cosine function, cos of omega t, let's say, the flux is a cosine function, then our back EMF, once we differentiate it, we'll get a sine function, right? So what does it mean? It is a 90 degree phase difference, right, between back EMF and flux. So from there, we draw our back EMF phasor and flux always 90 degree to each other, okay? In the PM machine, it is still the same. So this flux is your PM flux. So PM rotor is rotating, inducing a back EMF. So same, flux and back EMF are 90 degree to each other. And one thing we may want to note here is this flux is your rotor flux, okay? Coming from the, if it's a PM machine, it is coming from the PM. If it is a conventional synchronous machine, it's coming from your field current, okay? So this is your field flux or rotor flux, which gives me the back EMF EA. But once the winding current flows in the winding, it also induces a flux, right? So that's your stator flux, okay? So the stator flux is always in phase with your current, okay? So stator flux is phase with current rotor flux is perpendicular or 90-degree phase difference with your back EMF. Okay? The resultant flux actually gives you the terminal voltage. So when you have a motor, 90-degree to this resultant flux is your terminal voltage. So if we know the terminal voltage vector, we can find out where will be the resultant flux. If we know the back EMF, we can find out where will be my rotor flux. And if required, I can calculate out where will be my stator flux doing a vector diagram. Okay, these are all phasors or vectors. So that can be done. And because the stator voltage can be considered as the resultant flux, rate of change of resultant flux over equal to the rate of change of resultant flux. So from there, in fact, we can find out the equation, the basic equation, the phase voltage equation for the motor. Okay. The flux that is related to your stator current, the flux linkage that's related to your stator current is the voltage drop related to your inductance. L di dt is actually related to your flux induced by the stator current. Okay? And flux linkage related to your rotor flux is your back EMF, EA, and then you could have a resistance, okay, in the winding. So RAIA is just a resistive drop. So this equation, I think most of you are familiar with. This is the single phase voltage equation, okay, and it is a time domain equation, right? And we can express it as all of them as a phasor. Then we get the steady state voltage equation, which is based on which we have our equivalent circuit. Okay. Now here, one thing you should note is that this reactance or this inductance is not self-inductance or not mutual inductance, but the synchronous inductance, right? So what is the synchronous inductance? How it is different from self and mutual inductance. And this one we have developed for a uniform air gap synchronous machine. We haven't considered the salient pole case. So what is how the synchronous inductance is different from self and mutual inductance? Anyone remember? No? So let's look at where the synchronous inductance comes from. We have three phases, right? We said, and we will have self-inductance and mutual inductance. So the flux linkage related to the stator current of one phase should consist of inductance, self-inductance times the current of that phase, mutual inductance between the two phases, LAB, times the current in the V phase, and mutual inductance between A and C phase times the current in the C phase. So this is your flux linkage related to the stator flux. Okay? And for three-phase machine, the mutual inductance is actually, it's good that it's just equal to the minus half of the self-inductance. So if we replace the mutual inductance here, LAB and LSC, as half of the self-inductance, minus half of the self-inductance, and for three-phase balanced circuit, summation of IA, IB, IC is 0, So from there we can see IB plus IC is equal to minus IA. So replacing all this substituting these conditions back in our flux linkage equation, we will find that the stator flux linkage is actually 3/2 times self-inductance times the phase current IA. So this 3/2 self-inductance is the synchronous inductance, which includes the self-inductance and mutual inductance. Okay, that's your synchronous inductance. Its synchronous inductance includes both self and mutual inductances of your windings. And this is for your uniform air gap machine. But if we go to the salient pole type machine, we have two different synchronous inductance. The synchronous inductance at here, let's call it LD, and synchronous inductance here, let's call it LQ. LD and LQ are not equal. This is for conventional motor, okay? So why they are not equal? Their reluctances are not equal, right? Reluctances here and reluctances here and reluctances here are not equal, because in the D axis, air gap is much smaller, right, compared to Q axis. So small air gap means small reluctance is low. So low reluctance means you have a high LD compared to a large reluctance in Q axis, smaller LQ. So for conventional machine, conventional salient pole machine, LD is bigger than LQ. Now let's take the case of a PM machine. If you have a salient pole type machine, which one is salient pole? Let's go back to our these two rotors. So one is we call surface type, another one we call IPM. So one of them behaves like a salient pole machine and other one behaves like a uniform pole machine. Which one do you think will behave like a salient pole? IPM. So why the IPM behaves like a salient pole machine? Physically, if you see, if I put, this is IPM, right? This is IPM. So physically, if you see here, the IPM looks like a uniform air gap machine, right? Because it has the same uniform air gap everywhere. But IPM behaves like a salient pole machine. Why? Yes? Magnets are. So if I look at my D-axis flux, D-axis fluxes will cross like this. Okay? D-axis flux will cross like this. D-axis crosses the magnet. And remember, magnet's permeability is same as air, right? So it is crossing the magnet and the air gap. So it sees a higher reluctance. So that's why LD inductance is smaller for IPM machine and behaves like a salient pole machine. Okay? If we do the Q-axis flux, Q-axis flux will go like this. Go like this. This is the magnet, okay? This is the piece of magnet. So Q-axis flux does not cross the magnet. It simply circulates over top of the magnets, okay? So it's only crossing the air gap, not crossing the magnet. So it sees a lower reluctance. And because of that, LQ is higher. So it's opposite. That's what we have to remember. In a synchronous motor, conventional synchronous motor salient pole machine, LD is bigger. Okay? In an IPM machine, it behaves like salient pole, but its LD is smaller. And why smaller? We can understand from this flux path. Okay? So surface type, even though physically it looks like it has different air gap here will be smaller, bigger, smaller, and here it will be bigger, right? If we look, but again, the magnet's permeability is equal to air. So it has to cross a very large air gap all around. So it sees it as a uniform air gap actually, kind of. And LD and LQ is equal for SPM machine. Okay? So SPM machine or surface type machine behaves like a cylindrical rotor synchronous motor. And LD, LQ are synchronous inductance, okay? It is not self, not mutual, but synchronous inductance. And in this case, it is LD is equal to LQ. LD is less than LQ. Okay? In case of reluctance motor, same. This is because the structure is like a salient pole. So you will have LD not equal to LQ. And in reluctance machine, it depends how you define your DQ axis. So you can define DQ axis same way as a conventional machine, conventional synchronous machine, then we will say LQ is smaller than LD. But if you define the DQ axis same as a PM machine, then we will say no, LQ is bigger than LD. So for salient pole, DQ axis definition is kind of convention. You define it, how you define, okay? But LD is not equal to LQ, same as the IPM machine. So that's our inductance concept, that's our salient pole and non-salient pole. And then a torque equation. So as we said, it comes from the power equation, power, and then we find the power and then divide the power by speed to calculate torque in the conventional machines. So we could do the same thing also for PM synchronous machine, okay? We can find power, we can calculate out the both for salient pole and non-salient pole, or PM, SPM and IPM, we can use these two equations, the conventional equations. Only difference will be that your back EMF is coming from the magnet flux, and in case of the salient pole machine, XD will be smaller than XQ. So this traditional equation we can use also for PM machine. But why we don't often use this equation is that we need to know this angle delta, right? This load angle. So when we control PM machine, we don't control the delta angle. We control rather the current angle, okay? So that's why these two equations not often used, especially in control space, and they are also steady state equation. As you know, they are valid only for steady state condition. They cannot handle transient conditions. For transient condition, we need transformation. I think yesterday afternoon you discussed a lot about transformation, right? DQ transformation, why we need DQ transformation. So these conventional equations can handle only steady state. It cannot handle acceleration, deceleration, the transient condition. Okay, so that's why these equations are good to calculate steady state conditions, but not good for doing control. Okay, and in this equation of our salient pole machine, so this part, the first part, it has two parts, as you know, that the first part is very similar to the uniform air gap machine, right? And this part for PM machine is related to the magnet, because back EMF E comes from the magnet flux, right? Lambda PM, right? So the first part of the torque relates to the magnet flux. And second part, this part is known as reluctance torque, because it is due to the difference in reluctances, right? Why we have XD and SQ different. So that part is called reluctance torque. If we plot these torque characteristics versus delta, the load angle, you see that you get the peak torque when delta is equal to 90 degree. Okay, in case of a uniform air gap machine or SPM machine. In case of a salient pole machine, since we have the reluctance component, so the peak torque does not occur at delta equal to 90 degree. Usually it occurs at a lower than 90 degree. Okay, and if we make this E0, EA equal to 0, that means lambda PM is 0, we have this reluctance component, right? Which is the characteristic of a synchronous reluctance machine. And peak happens at 45 degree, about 45 degree. The reluctance machine, synchronous reluctance machine's peak torque occurs. Okay? So this is coming from actually all traditional equations, but they are equally valid for PM synchronous machine. Anything you would like to note down, maybe, is the time? And then we'll move to the PM machine. You want to take a break or at 12? Okay, so yeah, this will be the last section, next section, and then we will have the break at 12. But you take your time to note down what we discussed so far before we move to the next part. So in the next part, we have already discussed, but we'll again look at the PM machine. Especially we'll be looking at how it is different from brushless PM DC motor. What is the difference? And we will also try to see their classifications and their advantages. And we'll be looking at the recent advances of PMSM, that rotor design, rotor topology. Okay. So, surface type IPMSM we already discussed. We talk about why their inductances of D and Q axis are different already. And then you can see the reluctance machine, the new type of reluctance machine. Okay. If we use this rotor, which is, I think, quite common in switch reluctance machine, okay? Switch reluctance machines use a reluctance rotor like this. So if we simply use this reluctance rotor, the problem is you could have very large torque ripple. Okay, switch reluctance machine is quite well known for its noise, vibration, and torque ripple. Okay, so if we directly use a rotor like this, replace the rotor of a induction motor or a synchronous motor by a simple rotor like this made of only steel, the problem is, yes, it can work, but you may have very high vibrations. Okay, so to prevent those type of problems, then a new type of rotor was developed for synchronous reluctance motors. Okay, and you can see here the reluctance concept comes from the same concept of IPM. Okay, you have, instead of magnet, now we have these air gaps. Okay, it's kind of similar like a IPM machine, but instead of magnet, we are simply using air gaps, airs. Okay, so reluctance here compared to reluctance here will be different because you have to cross several of the air layers. Okay, so you have a large reluctance compared to Q axis where you are not crossing, you are crossing only the main air gap. Okay, so this synchronous reluctance motor behaves more or less like IPMSM. So if we understand IPMSM, we actually also understand synchronous reluctance machine. Okay, having many different layers help you to increase the ratio of XT and XQ. Okay, because for reluctance machine you only have the reluctance torque. So higher that ratio XQ over XT, the better it is. And these layers of different air gaps help you to improve that ratio. Sometimes you can also use magnets in the gaps. Okay, very small thin magnets, which is known as PM assisted reluctance motor. So PM assisted reluctance motor is actually IPM motor. Okay, only thing is it will have a larger reluctance torque compared to the PM synchronous motor. In PM synchronous motor, your magnet component is much higher than the reluctance component. Okay, that's the difference basically. So let's look at some evolution, how the PM machine was how it has come about. In fact, the PM machine has come about because of the problem of DC motors, brass. Okay, it's actually the main motivation was to eliminate the carbon brass of the DC motor. DC motor's dynamics, DC motor's control, everything was perfect. But the problem was the brass and carbon brass. You have to keep changing carbon brass every 6 months, which is a pain for industry, right? So they were trying to design something where you can eliminate the brass. And so the first version of PM machine is the PM brushless motor. Okay, and then how we control that PM brushless motor, based on that, in fact, we have the PM AC or PM synchronous motor. So construction wise, PM brushless motor and PM synchronous motor may look very, very similar. Especially PM brushless motor is nothing but a SPM motor. Okay, it is a SPM motor. Okay, stator, you can have distributed winding or concentrated winding. For cost cutting, often nowadays small brushless DC motor uses concentrated winding. Okay, but if it uses distributed winding, it will behave, if we control it with a sine wave inverter, it will behave like a PMS synchronous motor only. Okay, but the inverter, you will need the inverter and you will need the encoder. Okay, that's the main difference. Whereas in a brushless DC motor, you can use Hall sensors, and your inverter could be a much cheaper version of it, so that it produces only square waveform. Okay, so we have initially that PM synchronous motor, and under PM synchronous motor we have the IPM and SPM, and then later, this is in 2003, we have the concentrated winding concept for even for PM synchronous machine came out about. And why that concentrated winding concept come? They wanted to get flux weakening or constant power speed range also in the SPM. So SPM, there was no constant power speed range previously. If you have distributed winding, there is no reluctance torque. You cannot do flux weakening basically. Okay, so to make it suitable for traction application, the surface type PM motor, they wanted to have flux weakening. And one way of doing is to use that fractional slot concentrated winding type stator, and that led to a development in 2003 around. And later, same fractional slot concentrated winding was also used in IPM. Okay. The advantage of concentrated winding is for SPM is that it can allow it to have flux weakening and constant power speed range. But other advantage is that it is cheaper to make. Okay, and you can reduce the size of the motor with concentrated winding. So that's why it became later quite popular, especially in research area. Here you can see the difference of a BLDC, brushless DC motors concentrated winding, or it's sometimes called tooth-wound winding because the winding is wound on the one single tooth, as you can see. Whereas in a distributed winding, the windings are all around, right? Distributed in the slots. And same rotor, you can see. So when they use concentrated winding, usually the back EMF is trapezoidal, okay? But if you use distributed winding, you can get quite sinusoidal, line-to-line, especially line-to-line induced voltage, okay? So if we compare, for BLDC, the main difference is your line current is rectangular, okay? The inverter will produce a rectangular waveform, whereas for PMSM, current must be sinusoidal, okay? BLDC motor behaves very much like a DC machine, electronically commuted DC machine, and PMSM, we can analyze it using all the synchronous machine theory, okay? One more problem with BLDC is it could have very large ripple, torque ripple in the low speed operation. So it's good for low performance applications where you don't care too much about the torque ripple, vibration, etc. But they are not suitable for a traction application because you will have very large vibration or jerking if you want to try to use a BLDC in the traction. Okay, so that's why PMSM is more preferred for traction applications. So you can also see why that vibration is high. Okay, so you have the sinusoidal trapezoidal back EMF, you have a square waveform from your inverter, and the resulted torque has much larger ripple. It's not smooth DC. Smooth. You want the torque to be actually as smooth as possible for the motor, right? If you have ripple, that means your motor is doing like this, which is the vibration, right? So this ripple means that. And one more advantage of BLDC is that it can use Hall sensors, because you need to turn on and off these switches just where you want the back EMF and the current to be in phase with each other. So we just need to detect this 30-degree, and after 120-degree, this one 150-degree. So we just need to detect these positions, okay, to turn on your switch. So you don't need continuous position sensing. That's why you can use Hall sensors, okay? We are not doing a DQ transformation here. But if you want to do DQ transformation, that's what we discussed in the last afternoon. The transformation matrix need a theta angle, right? So that theta angle is actually your rotor position, and you must continuously detect that theta, okay? And so Hall sensor cannot do it. You have to have encoder. So that's and encoders is of course expensive. So compared to BLDC, that's why your inverter and control becomes more sophisticated, but you get a much more smooth torque. So here you can see how is the torque for a PMSM machine. So nearly smooth. Okay, it's more theoretical. In reality, it will not be this smooth. Of course, you still get ripple, something like this. Okay, if you do a finite element type, so you will be able to see those torque ripples. But if you use a Simulink type application, then you will see a very smooth torque, which is not actually the real case. Okay. So far, what we have discussed as a PM machine is radial flux type. Okay. So why we call it radial flux? Because the flux, magnet flux, coming out of the rotor is crossing the air gap radially, right? So that's why it's called radial flux machine. But there is another type of PM machine known as axial flux. So this is a rotor of axial flux machine. So the flux will cross stator. So this is your rotor, axial flux rotor, and this is your stator. Okay, let's say. So flux is crossing from rotor to stator. You may imagine here in this figure, they're coming out of the screen. Okay, and then you have the stator in front of it. So they're crossing axially, right? Compared to the radial flux, they're crossing axially. So that's why the name is axial flux. And axial flux machines are mostly surface type. As you can see, the magnets are glued on the surface. So they are surface type machine. And because they're surface type, they can be analyzed like a SPM machine, basically. Okay, all the control theory that you learn or all the other things that we learn can be applied to axial flux machine like SPM machine. But their design is far more complicated. So if you want to do an axial flux design, you will need 3D. 2D finite element will not give you the correct information or analysis. Okay, so axial flux design, you must have 3D finite element because you are looking at axially. Everything is happening axially, okay? So it requires the 3D finite element. But they are very good for power density improvement, okay? They have the highest power density, okay? Yesterday we talked about, they have the highest power density, and they are being proposed to use in racing cars, high-end racing cars, as a wheel motor, okay? Because they could be very, very small and very powerful. So uh, even though they are not proposed to be used in the main traction, but they are being proposed to be used in the racing car as a wheel motor. And I think Jaguar or somebody has already commercializing the axial flux PM machine as a wheel motor or as for their racing car version. Okay. So here you can compare some geometrical difference between surface type and interior type. And you can also see their advantages and disadvantages. Okay, I think we have already talked about the advantages or the but look at the disadvantages. For surface type, obviously we don't have the reluctance torque. It usually has very little flux weakening, the surface type. So they are not very suitable when you need large or wider constant power speed range. That's the reason why in traction application we do not see surface type. Okay, it's mostly IPM. So IPM has another advantage is that it is, since it is surrounded by the iron, so it also have relatively less demagnetization risk compared to a surface type. Okay, and because of the smaller main air gap, you can do flux weakening quite effectively through the armature reaction in IPM machine. So flux weakening and constant power speed range possible in the IPM, that's why. And but the control is complex, okay? Here, since LD is equal to LQ, often when you do the FOC, we keep the ID current equal to 0 and IQ current comes from your torque or speed command. Okay, torque or speed command. So control of FOC is relatively easy. But in IPM, ID is no longer 0. ID is not longer 0. You have to calculate ID, a particular ID value. So the control is usually much complex. Okay. Here you can see some comparison of the torque versus speed performance of a IPM and a SPM. Okay. One is operating, both of them are operating under maximum torque per ampere or MTPA. We'll talk about that later again, but you can see here. You can also see the flux weakening range. So for IPM, you could have a quite nice flux weakening range, okay? Whereas in SPM, it's almost nothing, and there's no constant power. Whereas in IPM, you can get a near constant power from, for this particular machine, it was from about 3,000 to about 7.5 thousand, okay? More than 2 times ratio. Here simply you are seeing the finite element flux path calculated by finite element, showing you how the magnet flux is crossing the air gap. So that's your magnet piece here. And for the IPM, here is it. Okay. So this is, you are seeing the d-axis flux. Okay, the flux is crossing the magnet. Now the innovation in SPM technology is, especially in the rotor, is not as much. Only difference, or only some innovation happened is by making, by shaping the rotor magnet. So compare this magnet with that one. So this is a square magnet, whereas this is kind of like a circular shape. So what's the difference? So by shaping the magnet, you may be able to reduce the torque ripple that we talk about. Okay, you can make the magnet flux more sinusoidal. So by doing that, you may be able to reduce some torque ripple. So that's the main innovation in the rotor. And there could be also a complete single ring type magnet for SPM. So this type of design is used for very, very high speed SPM motors, like 200, 300,000 RPM motor, and very small ones. Example is dentist drill, you know, the dentist drill, they use very, very high speed. So the motor that used in those type of applications is something like this. So very high speed. So you have a one single piece of magnet, like a ring or cylinder, and then on top of it you can have a sleeve, so that it gets a mechanical robustness. Okay, so the magnet are covered by a sleeve, a carbon fiber sleeve, to give it more mechanical robustness. And last but not least is the use of a concept called Hallback array. Okay, so Hallback array, what happens in all these other designs, your north pole is this way and south pole is this way. So magnetization directions are like this, right? For your piece of magnet. Whereas in Hallback type, one piece of magnet is magnetized this direction, the next piece is in this direction, the other one is something like this. So the direction of magnetization in each piece of magnet is different, and by doing that you can make the two things you can achieve. One is you can make the flux density as well as the back EMF more sinusoidal, and you can push more almost all flux to the air gap. So because all the flux goes to the air gap, you can eliminate any iron at the back. And by doing that, you can make the machine far more lighter, because you are removing iron. So Hallback array is proposed very much for the aerospace applications, because you can get lighter motors. Okay. And also Hallback array can be used in the axial flux type design. So if you use Hallback in the axial flux, you can eliminate the iron, so you get the lightest possible motor with that combination. Then the IPM, there is huge amount of innovation happened in the rotor. So many different types. Almost all automotive company have their own version of IPM rotor topology. Okay, for different regions. Okay, the double layers are to improve reluctance torque. Spoke type improves magnet component of the torque. V type, usually magnet component of the torque is improved. We developed this type, Y types, which combine actually spoke type with the V types through an optimization process, okay, in the finite element. So it's one of our patented design. And this rotor is more for the concentrated winding stators, IPM. And these are traditional ones, the flat types. Okay, I'm running battery running low, but we are almost finished. So some more varieties you can see for EV, Chevy, Prius, Camry, Nissan, Honda, Tesla. Okay, so many different types. And most of them are obtained through the finite element optimization. They have specific objective, so for those objectives lead them to this type of designs, okay, mostly for that region. And you may see that V shape is kind of becoming a norm for, because it can provide the flux concentration in the air gap the best. At the same time, it can give you the best possible reluctance torque. Okay, so V type has become quite popular. Okay. And then the advantage and disadvantage, we talk about distributed and concentrated winding, so you can see the difference between them. Why the concentrated winding can provide flux weakening also in SPM is actually the concept comes from here. It's called characteristic current. The ratio of the PM flux linkage over LD is equal to a current. And this current is sometimes it's called short circuit current and sometimes it's called characteristic current. So if the characteristic current and rated current is equal, then theoretically you can get infinite constant power speed range. Okay. So in using concentrated winding, in LD can be increased because of the they have larger leakage, and you can make this ratio equal to rated current or close to rated current or even smaller than rated current. Okay, and by doing that, SPM motor was able to actually also have flux weakening because you have the this characteristic. Okay. But concentrated winding, you do not get sinusoidal MMF. So you will have higher harmonics. So higher harmonics mean more eddy current loss, even in the magnets and the rotor. However, because these windings are kind of isolated from each other, so they offer very good fault tolerance. Okay, the mutual inductance is very, very low, so there is no mutual overlap between the phases, so that offers a good fault tolerance for the concentrated winding. Here you are seeing some of our work that we did for a IPM machine using concentrated winding and distributed winding. So this was our original, this was an original design, and this design we change it to by just doing some segmentation in the magnet. We were able to get or extend the flux constant power speed range for same stator, everything same, only changing the rotor by this. We extended it to the the power range was extended. So initially it was here. So by this design, it was extended up to there. Okay. And then when we use the concentrated winding and a V-shape, that CPSR was increased even further for a similar power rating. Okay, so This one's done at UNSW through various design optimization process, and we have these prototypes available. I think that's all for today. Next time when we come back, we'll talk about how to do this finite element design process. Okay? Tomorrow is a holiday. You can enjoy the holiday. And I think tea is available now, right? Yes, tea is ready. So enjoy the tea. So we'll finish for today. Okay? Thank you.